Today on How It's Made. Luggage. Tepees. Croissants. And rolling luggage. The best way to protect your bicycle against theft is a heavy-duty lock. A U-lock is the most secure option. Unlike a cable or chain lock, you can't quickly sever a U-lock with a pair of bolt cutters. It takes large, conspicuous tools, not something a thief can likely get away with unobserved. U-locks come in various sizes so that you can lock your bike to different structures, from thin bike racks to thicker tree trunks. The shackle and lock are made of hardened high-alloy steel, which is resistant to cutting, sawing, and twisting. To shape the shackle, workers load steel bars into a computer-guided bending machine. The machine applies more than 25 tons of force to bend the bar in the shape of a U. The machine also notches each end of the shackle. These notches are what receive the locking bolts. To make the steel hard enough to be tamper-proof, they send the shackle to an outside facility for heat treatment. This demonstration recreates a small part of that complex process, which is to heat the shackle to almost 1,500 degrees Fahrenheit to rearrange the molecular structure. Cool it in oil to set the hardness of that rearrangement. Then reheat at moderate temperature to restore the flexibility the steel lost due to the previous steps. When the shackle returns to the factory, a laser machine precision measures and, if necessary, corrects the dimensions as per specifications. Then the shackle is dipped in durable anti-corrosion paint. Once the paint dries, an automated machine slips a PVC tube over the shackle. Next, they screw a plastic bracket to one end of the shackle. This connects to a corresponding bracket you screw to your bike frame to mount the lock on the bike when you're cycling. The rectangular block that houses the locking system is called the lock body. It too is made of hardened steel. An automated press punches holes on the ends for the shackle and in the middle for the lock cylinder. The locking system has a housing in the center for the cylinder. Workers mount two metal plates over it. When you insert the security-coded key in the cylinder in turn, the cylinder rotates within the housing, and the plates move apart, triggering other components to lock the inserted shackle. The cylinder is made of brass, a relatively soft metal, so there's an impenetrable steel plate on top to prevent a thief from drilling into it. Workers give the cylinder grooves a squirt of grease, the housing as well. Then insert pins into the grooves. These act as blockers, preventing the wrong key from opening the lock. With the correct key, they give way, enabling the cylinder to rotate within the housing. This spring applies tension to the cylinder's steel and drilling plate, keeping it in position so that the key inserts easily into the cylinder. On each side, workers insert a lever and bolt. When you turn the key to the lock position, the lever pushes the bolt into the shackle's notch, immobilizing the shackle. This component spring-loads the bolt to prevent the inserted shackle from popping out prior to being locked. A pneumatic machine inserts the locking system into the steel lock body. A two-tone plastic cover gives the U-lock a snazzy appearance and makes the surface easier for the cyclist to grip. Here's how the lock works. When you turn the key, the cylinder rotates. This moves the two plates over it outward, triggering the levers on each side to hold the bolt in the shackle notch, locking the shackle in place. Every lock undergoes an opening and closing check. Random samples are subjected to more extensive quality control testing. It takes 13 tons of cutting force to break the steel, far more than even this larger-than-typical bolt cutter can apply. This torsioning machine measures how much twisting the U-lock can withstand. A bike robber would have to apply more than 350 pounds of force with a crowbar. The bike owner, on the other hand, needs only the coded key. The native North American teepee was designed to be a home where the buffalo roamed. Centuries ago, tribes were constantly on the move hunting the buffalo, which was their main source of food. Easy to pack up and reassemble, the teepee served as a portable shelter for this nomadic lifestyle. Today, people are rediscovering the appeal of a cone-shaped tent with a cook fire inside. And that's put the teepee on the comeback trail. No need to hand-stitch teepees anymore. Today, they produce them at a factory using industrial sewing machines. They start with the front panel. It's 3 layers of canvas and vinyl. They sew details like pockets for poles to open smoke flaps, and rectangular patterns to prevent stretching and tearing, from holes for lacing the front of the teepee together when pitched. The sewer now chops through the 3 layers of fabric with a chisel to make those holes. Another sewer stitches strips of buffalo hide to the door opening to make it more rugged. Using a pattern as a guide, the next worker cuts another panel on a slight curve. He then pieces together panel after panel to construct the rest of the teepee cone. He reinforces the hem with heavy nylon webbing. He tucks loops between the webbing and the fabric and secures them with more stitching. The loops will be used to stake the teepee to the ground. The team stretches out the completed teepee cover. An artist maps out some lines for painting on the fabric. There's 73 yards of it. It becomes a huge canvas for traditional artistry. The designs are Southwest American in style and highly symbolic. Circles can represent phases of the moon or the sun. A sample of the artwork has been drawn up beforehand for the client, and the artist refers to it as she works. She brushes exterior latex paint thinned with water around the perimeter of the designs. Then she soaks up paint onto a pad and presses it to the fabric within the painted lines. This avoids brush strokes and produces a flat finish that almost looks like dye. With the artwork complete, the teepee cover now makes a colorful statement. Outside, an employee shaves the bark off young trees to prepare the poles. There are 17 per teepee. Each one is 27 feet tall, the height of a 2-story building. A 2-person team now arranges 3 of the poles in a specific sequence to build the tripod that is the basic framework of the teepee. The assembler lashes the poles near the top with thick rope and a tight knot. He leaves a length of rope to dangle as they raise the tripod. The rope will come in handy later on. The arrangement situates the door pole east, towards the rising sun, and away from westward winds that could interfere with the cook fire. The team props up the remaining poles between the main tripod poles. The first 2 groups of poles form the front of the teepee, and a 3rd group forms the back. The assembler grabs the rope that still dangles from the central tripod, and from the ground, winds it around all the poles, where they meet at the top. The last pole is called the lifting pole. It's used to lift the painted teepee cover to the wood frame. They unbundle the cover and wrap it around the poles like a blanket around a person's shoulders. Once the fit is nice and snug, he laces the front panels together using willow branches for lacing pins. There are 18 pins in total, fastened above and below the doorway. He pegs the canvas to the ground and then installs 2 last poles for opening and closing the smoke flaps from the ground. Traditional in design, with modern-day materials and construction, the teepee is still an idea worth pitching. Croissant is the French word for crescent. This flaky curved roll is generally associated with France, even though many food historians believe its origins are Austrian. Regardless of where it came from, the croissant is a popular breakfast pastry in many parts of the world. Plain, with jam, or dipped in a cup of coffee, there's nothing like the light, flaky texture and buttery flavor of a croissant. This commercial bakery makes its croissants with soft spread margarine in lieu of butter. The other ingredients are yeast, very cold water, because warm water would trigger the yeast to react prematurely, sugar, a touch of salt, and white all-purpose flour. All the ingredients go inside an industrial mixer for 10 minutes. First at slow speed to blend everything and form the dough, then faster to knead it. Next, the sticky elastic dough enters the multi-roller machine. As an automated dispenser lightly dusts the dough with flour to prevent it from sticking to the equipment, a series of 16 rollers progressively flattens the dough into a thinner and thinner sheet. The next process, lamination, is what creates the croissant's flaky layers. The first station on this line extrudes 44-pound blocks of margarine into a 2/10 of an inch thin sheet. The next station lays the margarine sheet on top of the thin dough sheet, then folds the ends of the dough upward, enveloping the margarine. Then rollers compress the overlapped dough ends to seal the margarine inside and flatten the whole thing down to about 4/10 of an inch thick. The next station repeatedly folds the dough over itself. Then, with rollers again, presses the layers into a thin sheet. This laminating cycle repeats over and over again until each dough block coming off the line comprises 243 layers. Plastic wrap keeps the dough moist, as it now undergoes 8 hours of refrigeration. The cold rehardens the by now softened margarine and lessens the dough's elasticity. The dough is now ready for the automated machine that forms the croissants. The first rollers progressively flatten the connected blocks into a thin sheet. Then another roller runs over the dough horizontally to expand the sheet to the required width. Next, cutters divide the sheet into 7 thin bands, each one 4 inches wide. Then a roller surfaced in triangular blades cuts each band of dough into triangles. A robot separates the triangles and turns them all in the same direction, with the flat side forward. A stopper running the width of the conveyor belt aligns the triangles in straight rows for the next station, inside which a device rolls each triangle into the shape of the croissant. The bakery's 2 forming machines output 50,000 raw dough croissants per hour. Next stop, the proofer, a steam chamber inside which the heat and high humidity activate the yeast. The dough rises, and by the time the croissants exit an hour later, they've doubled in size. They now bake for 14 minutes in a tunnel oven at a temperature of 350 degrees Fahrenheit. The moisture in the dough evaporates, the resulting steam, along with the melting margarine, producing air bubbles which separate the layers, creating that signature flakiness. The croissants are now fully baked, golden brown, and fragile. Soft rubber suction cups delicately transfer them to a conveyor belt. The belt leads to a spiral tower. By the time the croissants descend to the bottom, they've completely cooled. As they travel to packaging, a quality inspector pulls any misshapen croissant. A multitasking robot slaps an adhesive label on plastic bags, counts out and drops in 24 croissants, then securely seals the bags to lock in the freshness until the croissants reach your breakfast table. Thousands of years ago, someone invented the wheel. In 1970, this fundamental invention was applied to luggage thanks to an American luggage executive who came up with the concept while carrying heavy bags on a trip. By the 1980s, virtually all luggage had wheels. Today, we take rolling luggage with us everywhere we travel. They take the heavy lifting out of a trip, so it feels more like a vacation. These hard-shell rolling bags start with polypropylene pellets. It's a synthetic material. They add a small amount of colored polypropylene pellets to the uncolored ones. They'll act as a dye for the batch. They allow the mix to dry for an hour, getting rid of humidity that would freeze in icy temperatures and cause the luggage to fracture. They mix and melt the polypropylene pellets into a thick blue liquid. Then it's over to the injection molding system. The molds close, and a nozzle injects the liquid polypropylene. The molds are equipped with a cooling system so that the polypropylene hardens almost instantly into a lightweight yet durable material. A pile of pellets becomes half of a luggage shell in mere seconds. A robot transfers the molded shell to the next station. An employee glues the company logo into a slot. To ensure it really sticks, it's over to the logo machine. It uses hydraulic energy to press the logo firmly into position. He now screws the service handle into its molded slot. This handle is for those times when the traveler has to lift the bag by hand, upstairs, or onto a baggage belt. These triangular molded parts are the side feet. They'll keep the luggage upright. He fastens them onto the base of the shell. It's time to close this bag. He adds the other half. He threads a steel rod into hinge holes to hold the two shells together. Next, they mold wheels from nylon. A robot transfers the wheels to another part of the mold. The mold closes, and a nozzle pipes in hot liquid rubber to apply it to the rolling surface of the wheels. The rubber adheres to the nylon and solidifies. They attach two wheels to a polypropylene hub for stable swiveling action. A factory worker now inserts an extendable handle. Then, working from the inside, she screws the handle to the luggage shell. She reinforces the connection with a metal bracket, ensuring that the extendable handle will hold fast, even when the load is heavy. She plugs the wheels into their slots in the base of the luggage. She secures them with screws. This bag is now mobile with 360-degree swiveling action. The next employee installs this water-resistant rubber piping. It will seal the bag and keep the rain out. She presses it onto the edge of one of the shells. She attaches brackets for hanging dividers to the other shell. She snaps 3 side locks and 1 central combination lock onto the bag. She screws down the hanging divider brackets. The fabric liner with its zippered pockets goes in next. The elastic dividers extend from it to attach to the brackets. It's time for the tumble test. A technician places the luggage in a rolling steel drum and it bounces around. They conduct this test on a random bag every now and then to confirm that the luggage will bear up to rough handling. And with that, these bags are ready for a vacation. If you have any comments about the show, or if you'd like to suggest topics for future shows, drop us a line at sciencechannel.com/howitsmade.